Hello everyone, today I will introduce our work Starry, which is a semi-lead commit protocol for multi-master transaction processing. The authors are from East China Normal University and Huawei. Firstly, I will introduce the background. Many cloud databases disaggregate the computation and storage into separate layers, so that both layers can expand and shrink up independently. For example, OLTP databases like Aurora, PoloDB, and OLAP databases like Snowflake AnalyticDB, they both adopt the disaggregated storage architecture. In this paper, we will focus on how to improve the performance of transaction processing on the disaggregated storage. For the disaggregated storage, the ideal transaction processing model should have these characteristics. Firstly, scalability. The computing layer should support adding additional computing nodes to execute transactions concurrently, which is usually called multi-master transaction processing. The second is high availability. Strongly, multi-master transaction processing can enhance the availability of computing layer. As for the storage layer, it should maintain multiple replicas. This requires a consensus protocol for log replication. The third one is strong consistency. Strong consistency requires both serializability and linear readability. This requires that consensus protocol and the concurrency control protocol should work together. So in this work, we will investigate how two protocols collaborate to better support multi-master transaction processing. To answer this question, we first describe the multi-master transaction processing on disaggregated storage. In the storage layer, there are a set of data shards, and each shard has a group of replicas. The replicas can handle requests from the computing nodes, include the read and write requests, and as well as transaction commit requests. The computing node is responsible for handling requests from clients and execute transaction logic. So when computing nodes receives the request from users, they will execute the transaction and read data from the storage layer. Then the new writing values are stored locally. After execution, the transaction enters the commit phase. The computing node will generate a log entry to record the transaction's writes and send the log to the storage layer. The storage layer will replicate the log entry and perform concurrency control to validate if the transaction can be committed, and finally return the commit result to the computing node. However, when multiple computing nodes execute transactions concurrently, a big challenge is how to handle conflicts among computing nodes. For example, T1 and T2, they are in conflict. So when the replica detects the conflict, how can they resolve them? A simple choice is to about one transaction, but how to ensure that replicas make consistent about decisions, because they may see transactions in different orders. The other choice is that let the storage layer coordinate to reach a consistent order, but this requires additional coordination, which is much more costly. Based on different consensus protocol, we summarize two committing patterns. They differ dramatically in conflict resolution efficiency and performance. The first one is leader-based committing. It's built on leader-based consensus protocol like Raft. In each shard, a replica acts as a leader. Only the leader can process requests and make the committed decision. This means that only the leader can perform validation and resolve conflicts. Such a centralized conflict resolution is efficient because it will not cause divergence. For example, when the leader receives two transactions, it orders T2 before T1 and decides to commit T2 and abort T1. But only the leader can handle requests may cause the leader to become the bottleneck. And in the cross-region deployment, the computing node contact with the remote leader will introduce multiple rounds of communication. That had a huge penalty on the performance. The other committing pattern is leaderless committing. It's built on leaderless consensus protocol. In leaderless committing, each replica can make committed decisions independently and tries to reach consensus about the decision. But this means that when conflict occurs, the conflict resolution is also decentralized. For example, the replica may receive commit requests of T1 and T2 in different orders and make different decisions. The replica in region 1 decides to commit T1 and abort the T2, and the replica in region 2 decides to commit T2 and abort T1. In this scenario, both T1 and T2 cannot reach a consensus on the committed decision. They will both be aborted. But decentralized committing is good for performance, since the load can be balanced on all replicas, and each computing node can be served by a local replica. So the cross-region communication can be reduced. In the conflict-free scenario, a transaction can be committed in only one cross-region communication. So how to ensure both performance and conflict resolution efficiency? We noticed that centralized committing is good for conflict resolution, and decentralized committing is good for performance. Our basic idea is to integrate two committing patterns into a single protocol. So we proposed the semi-linear commit protocol. By introducing a centralized node named sequencer, we can offer two paths for committing. The first path is for non-conflicting transactions. For example, in the non-conflict path, each replica can make the computing decision independently. For example, T1, T3, and T4 are non-conflict. They can pass the validation on all replicas and reach a consensus in only one cross-region communication. The other path is for conflicting transactions. If a conflict occurs, after replicas detect conflicts, they will deliver the conflict dependency to the centralized node sequencer. It's also the semi-linear. Then the sequencer will reorder conflicts and make new committed decisions and return the decision to the computing nodes. Here illustrate the message flow when conflict occurs. R0 and R4 replicate T1 and T2 to other replicas. In R3, T2 is received first. So when it receives T1, T1 is identified as a conflict. Conversely, on R1 and R2, T2 is recognized as a conflict. Once a replica detects a conflict, they will deliver the conflict dependency to the sequencer. And because R0 and R4 cannot receive a consensus committed decision, so after one round of communication, both T1 and T2 cannot commit yet. And R0 and R4 will send a request to the sequencer to ask for the new committed decision. Upon receiving the first request, the sequencer will reorder the transaction and then send back the new decision to R0 and R4. In this case, the sequencer decides to commit T2 and recommit T1, so no one is aborted. The goal of reordering is to find a serial order for conflicting transactions, where aborting as few transactions as possible. The reordering strategy we designed is based on an observation. In our work, we only detect read-write conflicts. And for read-write conflict, if the write transaction is ordered after the read transaction, the order is a serial order. Here is an example. T alpha and T beta are read-write conflicts. Based on their timestamps, T alpha is ordered before T beta. So in this case, T beta has to be aborted. But if we order T alpha behind T beta, both transactions can be committed. So the sequencer will collect read-write dependencies and build a dependency graph. And when receiving a request for the decision of a conflicting transaction, the sequencer will find all relevant transactions to this one and resolve them in a batch. The sequencer will first find all strongly connected components. If a strongly connected component consists of more than one transaction, it contains a dependency cycle. The sequencer will choose to break one transaction to break the cycle. Here, the sequencer choose to abort T4 and T6, and after aborting them, the remaining there is no dependency cycles anymore. For the remaining transactions, the sequencer will topology sort them and get a new order. If a transaction's timestamp violates the new order, the sequencer will assign a new timestamp for it. In this example, T3, T5, T8 can be committed, and the T1, T2, T7 are assigned new timestamps and recommit. More details can be found in our paper. We evaluate the performance of Starry with Retreat and YCSB workloads. We compared it with leader-based committing that built on Raft and the leaderless committing method, Tapper. The experiments are conducted on both local cluster and Alibaba Cloud. These two figures demonstrate in the local cluster, our semi-leader commit protocol achieves 5.1 times and 1.4 times improvement in throughput compared to leader-based and leaderless committing, and reduce the abort rate by more than 60%. This is because our centralized conflict resolution can avoid a lot of unnecessary aborts. Under high contention, our semi-leader protocol also outperforms leader-based and leaderless committing significantly. On the cross-region cloud, our semi-leader protocol can reduce the transaction latency by more than 50% than the leader-based committing. And it also achieves significant improvement in throughput than both leader-based and leaderless committing because our effective conflict resolution strategy. Finally, conclude our work. We proposed a Starry, a multi-master transaction processing mechanism that built on semi-leader committer protocol. It combines decentralized transaction processing and centralized conflict resolution. Experimental results demonstrate that it can improve the performance in terms of scalability and latency compared to leader-based committing, and it can also reduce the abort rate compared to the leaderless committing. Here is our presentation. Thanks.